But yeah, let's see what we are doing today. All right, so now we are on 8.4. So starting now, we're gonna go through stuff for the last exam. 8.4 is other convergence tests. So we've actually done quite a few of these tests over like the past couple of weeks. And we're pretty much at the end now. So there's 3 more tests that we have to learn, and they're all gonna be part of 8.4. So I guess let's just test how much you guys remember. Who remembers the tests we've done? So everyone, can you just list out a few tests that we've done so far? Comparison test, yep, that's one of them. Integral test, yep. Divergence test. The comparison test works for series and integrals, right? Yeah. Anything else? Yeah, I think you guys pretty much got most of it. There is also the one where we sort of manipulate a geometric series. It technically is not a test, but it's sort of like another method that we learned. P series. P series is not a test. It's more of like a tool we use within a test. So, but yeah, P series is another thing we covered. All right, so good. You guys pretty much remember a lot. Okay. So let's look at what we're going to do today. All right. So revisiting alternating series. Alternating series, we've seen these before, right? Alternating series are series where as you go from one term to the next, you switch signs. So you can tell an alternating series is an alternating series when you have the -1 to the power in the front. So you can see the notation here. It can be written in 2 ways. So the first way is -1 to the nth power times b to the n, or -1 to the n+1 power times b to the n. So both of these forms are alternating series. It's just that one of them starts with a positive and the other one starts with a negative, and then they both alternate. Okay, so we're going to start off by looking just at some few examples. And this is what we're going to do. So we're going to identify what is b of n in each alternating series. Okay. So looking at the first example, we have the series from 1 to infinity of -1 to the n over n squared. So just by looking at that, can you guys tell what b of n would be in this series? N squared? 1 over n squared? Yeah, so it would be 1 over n squared, right? It wouldn't quite be n squared because it's in a denominator, so it's 1 over n squared. Okay, and then because it's -1 to the n, the first term is going to be negative because the index starts at 1. All right, what about the second series? What is b of n in the second series? One over square root of n plus 5. Yep, very good. So that's b of n in the second series. And then last but not least, the third series. So what would be b of n in the third series? 1 over n. Yeah, it is 1 over n. So 1 over n is the b of n part in the third series. One comment about this third series, notice how the exponent is n plus 2, right? So if you look at the forms we have on top, it's written with the exponent of either n or n plus 1. But here we have an exponent of n plus 2. Does that bother you guys? It bothers you? Okay, well, all right. Is there anything you can do to make it look like the forms we have on top? Index shift? Um, yeah, you could. You could index shift. But there's actually like another way without doing index shift. Because if you do index shift, then you're gonna like change the denominator and then stuff happens and then the index changes. There's actually a way to do this without changing anything. Just changing one thing. So the hint is that it's a -1, right? So when you like times -1 by itself, it just goes from -1 to +1 to -1 to +1. So what you can do is actually, instead of writing -1 to the n plus 2, you can just write the following. Let me just show that. Okay, so this would be equal to the summation and goes to 1 to infinity of, and so instead of writing -1 to the n plus 2, I can just write n. That is actually the same thing. Can you guys see that? Because the only thing that the -1 to the n plus 2 does is it alternates the signs. So as long as you start with the same sign when you rewrite it, it's the same thing. Okay. And likewise, if I had something like a -1 to the n plus 3, this will be equal to -1 to the n plus 1, right? Given these are both series, and you get that idea. All right, so that's revisiting alternating series. And this is going to prepare us for the next test that we are about to learn. So the next test is called the alternating series test. Okay, so let's see what this test says. So it says, suppose you have an alternating series, which is what we just looked at. Then if, so two conditions. If number one, the limit of b of n as n approaches infinity goes to 0, and then the second condition is if b of n is a decreasing sequence, then you can say that the alternating series is convergent, okay? So recall that b of n is basically the part of the series that's like not including the alternating sign part. So basically ignoring the -1 to the n part. All right. So before we look at some examples, just a couple of notes about this test. Number one is that if this test fails, you cannot just say that an alternating series is divergent, okay? If it fails, then you say it's inconclusive and you have to go on to use another test. And then the second note is that regarding condition number 2, when we say b of n is a decreasing sequence, so it doesn't have to be decreasing all the way. There are some sequences where like they increase first and then they decrease. And that's actually fine too. So as long as B of n is a sequence that's eventually decreasing, then condition 2 is satisfied. All right. Okay, so I'll just give you guys a couple of seconds to jot that down, and then look at some examples. All right, so let's look at these examples here. Okay, so number one. Well, first of all, directions say determine if the following series converge or diverge. Okay. So taking a look at the first example, we have a series from 1 to infinity of -1 to the power of n plus 1 divided by n. Okay. So just for reference, I'm going to copy the alternating series so we can look at it while we do the problems. Okay, let's put it right there. So is everyone convinced that the first example is an alternating series? Sure. So it's alternating because we have the -1 to the n plus 1, right? And then can you identify B of n in this question? Yeah, so B of n in this case, use a different color. So B of n in this case is 1 over n. All right. So first thing we need to see is why isn't it -1 over n? Yeah, so we separate it like so. Let me write it on top here. So it's the summation of n equals 1 to infinity of -1 to the n plus 1 times 1 over n. That's how we separate it. So that means B of n is the 1 over n part. Okay. All right. So let's check the two conditions. Number one, does the limit of B of n go to 0 as n approaches infinity? So yes or no? Yes, right? So limit of 1 over n as n goes to infinity is indeed equal to 0. So the first condition is satisfied. And then number two, is B of n a decreasing sequence? So consider the sequence 1 over n. So if you were to list out the terms of 1 over n, is that a decreasing sequence? So let's list it out right now. So this would be 1 over 1, 1 over 2, 1 over 3. So this is good, right? this is indeed a decreasing sequence. So therefore, what can we conclude about this series here? Yes, it is convergent. So this converges. And you can say by the alternating series test. All right. One comment I want to make is that we sort of just like verify the conditions just by like observation and writing things out. So nothing was like really formal. But regarding condition 2, when they say to find out whether it's a decreasing sequence, sometimes it might not be obvious as to whether something decreases just by writing out the terms. So do you guys think you know a way to formally show that a sequence is decreasing? So how can we formally show that a sequence is decreasing? Would you take the derivative slope if the denominator increases? Yeah, so the derivative part was basically what I was going for. So when you want to verify that it's decreasing, you can sort of think of it as like a function. So how do you verify that a function is decreasing? You have to take the derivative, but then what do you have to do with the derivative? Do you guys remember? So if a function is decreasing, what does that say about the derivative? Yeah, so you have to make sure that the derivative is negative, all right? For this one, I don't think we need to do that because 1 over 1, 1 over 2, 1 over 3, that's obviously decreasing. So here it's not too necessary, but for questions where it's not that obvious, then you do want to take the derivative and make sure it's negative, okay? All right, let's move on to number 2, or the second example. Okay, so let's look at this one. You guys can see that it's a alternating series, right? Yes, okay, because the negative 1 to the n is there. All right, so it's an alternating series, which means we should probably try the alternating series test. First thing we want to see is if b of n goes to 0. So really quickly, what's b of n here? One over n squared plus 5. N squared over n squared plus 5. N squared. Yeah, so make sure you rewrite it if it's not obvious. So this is negative 1 to the n. That's the alternating part, which is not part of b of n. So b of n would be basically the rest, which is the n squared over n squared plus 5. So this is B of n here. Yeah, so as long as the alternating part is basically -1 to the n or -1 to the n plus 1. If it's anything other than that, you can just rewrite it as like -1 to the n or -1 to the n plus 1. All right, so what's the limit here? This is 1, right? So the limit here is 1. Two ways to show that. You can either just say, oh, because they're the same degree, you just take the coefficients of the leading terms, or you can just divide everything by n squared, and that'll also give you 1. So the limit here is 1. So what does that mean? Divergence? Inconclusive? It means nothing. Yeah, so be careful about what we said about the alternating series test. We said that if the alternating series test fails, then the test is inconclusive, okay? So at this point, yeah, you're right, this means nothing. This means inconclusive, which means we still don't know whether it converges or diverges. So we have to use another test, basically. I mean, you don't have to use another test. You can, use any skills to your advantage of finding whether this converges or diverges. I can sort of see a logic to reach a conclusion. Do you guys have anything, like looking at it, do you guys think you can reach a conclusion? So the limit goes to 1, right? And then we have the alternating part, which is the -1 to the n. Putting those two pieces of information together, do you guys see what this would sort of go to? Since it doesn't approach 0, it will diverge. Well, the fact that it doesn't approach 0 means that it failed the alternating series test, which that in itself doesn't mean that it diverges. So it does go to 1 if you ignore the alternating part, but consider the graph. So if I was to draw this, this series in a graph, so we know that as we go further and further into the series, we are we're just adding a bunch of 1s, right? Because that's what the limit goes to. So if we were to go towards 1, and then we consider the fact that it alternates, your graph will look something like this. So here's 1, here's -1. So as you go further and further in, you'll have 1, -1, 1, -1, 1, -1, and it'll get closer to 1 and -1. So based off of this, can you guys see what the answer would be? Yeah, so this would be divergence, actually. Yeah, it's basically the divergence test. So the divergence test says that if it doesn't go to 0, then it's divergent. Okay, so this is divergence. by divergence test. All right, so just the summary of this. So first we tried the alternating series test and it failed, which means we didn't know whether it converge or diverge. But then when we use the divergence test, then we know that it diverges, okay? All right, example number 3. So this one says series as n equals 2 to infinity of cosine of n times pi over square root of n. So is this an alternating series? Certainly doesn't look like it. What do you guys think? Is this an alternating series? Don't think so. Yeah.
I think it is.
Let me just clear up the space here. You think it is an alternating series?
Yeah, because it had -1 to the power of n.
How so? It's a cosine though.
Oh wait, this question. Oh, never mind. Sorry, I thought you were talking about the other one.
Oh yeah, okay, that's fine. Yeah. So we're looking at this one right here, cosine of n times pi over square root of n. You think it is because cosine alternates between -1 and 1? Really? Interesting. Let me just see if that's true. So the first index is n equals 2, which gives you cosine of 2 pi. What is cosine of 2 pi? It's cosine of 0, which I think is 1. Let me just make sure that's correct. So 0 is over here. The coordinate here is 1, 0. Cosine is the x value. Yeah, so it's 1. And then when n equals 3, that gives you cosine of 3 pi. 3 pi is over here. It's on the other side of the circle. This is -1, 0. Okay, so that gives you -1. All right, yeah, I think this is an alternating series. Do you guys see what I just did? So as the index goes on, you're basically moving back and forth between 1 and -1 because of the way that cosine works on the unit circle. So you can actually rewrite it then as an alternating series. So the first term is just +1, so I can just start it at -1 to the nth power. Okay. So this is our series now. All right, well, since it's an alternating series, let's use the alternating series test. What is B of n here? Yeah, so it's just 1 over square root of n. And then when you take the limit, does this go to 0? So the cosine doesn't matter. Well, it's not that it doesn't matter, it's just It's just because of the way the cosine values came out to be, it was technically an alternating series. Because cosine of 2 pi was 1, and a cosine of 3 pi was -1, and a cosine of 4 pi would be 1 again, and then it would just, go back and forth. So I just rewrote it just to make it look like an alternating series. Which two forms? I talk about the two forms of the alternating series. Well, one of them just starts at and the other one starts at n+1. You have to choose the form that sort of like matches the sign of your first term. So here our first term was +1. This is our first term here, which means you want to choose the form that gives the first term to be positive, which was this one here, the first one. Because the index starts at 2, so -1 to the 2 power would be positive. So that's why I chose that one. Yeah, all right. So the limit here is 0, right? Because as n gets bigger, the denominator gets bigger, which makes it 0. And then 1 over square root of n, is that a decreasing sequence? Pretty sure it is decreasing, right? Let me just check using a graphing tool. Okay, yeah, so according to the graphing tool, this is what the sequence looks like. You can see that it's decreasing, so this is fine. If you wanted to show it algebraically, you would just take the derivative and then show that it's negative. But yeah, so this is fine. Therefore, we can say that this series here is convergent. This is convergent. Okay. All right, so that's the 3 examples that we have. Any questions on any of those? Okay, so if there's no more questions, I will have you guys try some on your own. Yeah, what's up, Devin? If the test fails, it can only mean it diverges. No, not necessarily. So if the test fails, we say it's inconclusive, and you have to use another test to see whether it converges or diverges. It is possible that it can fail the alternating series test and it can still converge. So yeah, don't assume that it diverges if it fails. All right, so I'm gonna give you guys 6 minutes to do these 2 examples here. So try these. So what did you guys think of the test last Thursday, by the way? Did you guys think it was better than the first one or worse than the first one? Like in terms of difficulty, did you find it more difficult or less? Seemed about the same, hard of affair. Yeah, I will say that the topics are totally different because, you know, the first one was just like techniques of integration, and then we moved on to like all these tests. Okay. Easier than some of the homework. Yeah, I mean, yeah, I've looked at the homework problems. I mean, I'm not the one who makes the homework problems, so usually what happens is I just take a look at it, and yeah, some of them do seem a bit harder than what is necessary, but at least it's good practice. How are you guys doing on the questions? Deal with the negative power. Uh, Negative power. Oh, where's the negative power? Second problem. 2 to the negative n. Uh, it's oh, negative 1 to the negative n. Oh, I see. Yeah. There's a way of dealing with that. We'll go over that. All right, let's go over it now. So switch. Let's do the first one first. So regarding the first one, first thing I noticed is that it's negative 1 to the n plus 6, which is not the form we are given in the beginning, but we can rewrite it, right? So if I want it in the form of like negative 1 to the n or negative 1 to the n plus 1, which one would I rewrite it as? Yeah, so this is the same as negative 1 to the n, right? Because the first term is positive, so whether you say n or n plus 6 doesn't really change that. Times n over n squared plus 9. All right, cool. So it's an alternating series. What is b of n here? N over n squared plus 9. Yep. So does the limit go to 0? As yeah, does it go to 0? Yes, right? So this is 0, so that's good. And then now we need to verify that this sequence is a decreasing sequence. So n squared plus 9. So is this decreasing? Yes. How do you know? So let me just list out a few terms. So the first term is n equals 0. So that gives you 0 over 9. So that's 0. and then denominator is higher power. Okay, so you have to be careful there because if the denominator is higher power, what that usually says is that denominator is bigger than the numerator, but that doesn't mean that the next term is actually less than the previous term. Shouldn't we look for the first term to be negative? I'm not sure what you mean by that. Could you clarify? I'm going to continue listing out the term. So when n equals 1, we have 1 over 10. When n equals 2, we have 2 over 4 plus 9 is 13. Yeah, I don't know. This doesn't look decreasing to me. Keep going. Okay. 3. 9 plus 9 is 18. Okay, yeah, this isn't obvious as to whether it's decreasing or not. I mean, maybe you'll do it later. Because it went from 0 to 1 over 10. That's not decreasing. 4, 16 plus 9 is 25. Yeah, I can't really tell. I'm gonna have to, let's go ahead and take the derivative. So, the derivative, well, you need quotient rule, right? So it would be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay, so that's the derivative. Let's see if we can show that it eventually has a negative derivative. So we should probably simplify this. So this is n squared plus 9 minus 2n squared over n squared plus 9 squared. So this is negative n squared plus 9 over n squared plus 9 squared. Okay, so that's our derivative. Do you guys see what the critical points are here? So critical points, remember, they're points that make the derivative 0 or undefined. Yeah, so 3 and -3, right? Those are your critical points. We can just ignore -3 actually, because -3 wasn't even part of our index starts at 0, so we can just ignore -3. So the critical point is going to be 3, and then we just need to test that the derivative eventually becomes negative. So let's just test this side over here. So if I choose something like 4, if n equals 4, what does that make the derivative? So that gives you -4 squared plus 9, or 4 squared plus 9 squared. So this is -16 plus 9, and then this is something positive. Yeah, so the derivative is negative here. Okay, great. Yeah, that's pretty much all we needed. So from this, we can say that the sequence eventually starts decreasing. So yeah, basically what was happening was the sequence was increasing all the way up to 3, and then starting from 3, it started decreasing. So we can say that condition 2 is satisfied from the alternating series test. Okay. So we can say that this series converges. So of course you didn't really need to do all that. What you could have also done was just observe the graph. Let me see if I can show you guys what the graph looks like. This is, all right, so here was the graph apparently. Yeah, so you can see that starting at 0, it was actually increasing, and then at 3 is when it starts decreasing. So that's fine. That satisfies our condition. All right. All right, let's move on to number 2. So someone had a question saying that they didn't know how to deal with the -1 to the n in the denominator. Does anyone have a solution for that? Bring it up as 1 to the -n. Yeah, I mean, we could. So you could write it as -1 to the -n over this stuff. But like, if you do that, then the exponent is -n, and that's not really like the form we want. So I don't know. Let me propose a let me propose another step, and then you guys tell me if I'm able to do this or not. So going back to the original question, what if I rewrote it as -1 to the n over 2 to the n plus 3? Can I just do that? What do you guys think? So the reason why I wanted to try this is because if I gave you a fraction, right? Like if I gave you like 2 over -3, this is the same as -2 over 3, right? So that's basically like an explanation of why I can do this. You know, like it doesn't matter where the negative sign is, whether it's like in a denominator or a numerator. It's still the same thing. So I can write it like this, but yeah, there's multiple ways of like getting towards that. I know some of you wanted to do like some algebraic manipulation, which is fine. You should still reach the same conclusion. But we'll stick with this because it's already in the form of a alternating series that we are familiar with. Okay, so yeah, -1 to the n over 2 to the n plus 3 to the n. What is b of n here? So does this go to 0? Yeah, because the denominator goes to infinity. Okay, and then is this decreasing? So the sequence right here, 2 to the n plus 3 to the n, is it decreasing? I think it should be decreasing, right? Let me just list out some terms just to make sure. So when it's 0, you get 1 over, that's 1 plus 1 half, 1 over 2 plus 3, 1 over 4 plus 9. Yeah, this is fine. This is definitely decreasing. Yeah, okay, cool. So this also converges. All right, are you guys good? Yeah, okay. So that's the alternating series test. So like every single test here, we're not gonna go through the proof because I don't think any of you guys care, but they're on the internet if you're curious. I know that we've been going over a lot of these tests and it might be a little overwhelming because you might be faced with a problem and you might say, well, I don't know which tests to use. So don't worry about that too much for now. When we cover all the tests, we're gonna go through a little summary of like what question you should ask when you're approaching a problem to sort of like narrow down which test to use, okay? So for now, just try to get familiar with each test and how to use them. Okay, moving on. So I said in the beginning that we have 3 more tests to cover in this section. We went through 1. We're probably not going to go through all 3. I would say we're probably going to go through 2. So yeah, we'll probably continue this, or we'll break this up into 2 lectures. But let's see what we have next. Okay, so we have some definitions. So what are these definitions here? They are absolutely convergent and conditionally convergent. So let's read what these definitions are. So first one, a series is called absolutely convergent if when you take the absolute value, it is also convergent. And then if a series is convergent, and then when you take the absolute value, it's divergent, we call it conditionally convergent, okay? So do jot down those 2 conditions, or those 2 definitions. And then we have one little note here, and it says fact. So if a series is absolutely convergent, then it is also convergent. So from that fact, you can sort of say that like absolutely convergent is like a stronger form of convergence. I guess you could say it like that. Okay, because if something is absolutely convergent, it is also regularly convergent. So just take a moment to jot those down. Yeah, so basically to test these things, we just take the absolute value and see what happens. So let's look at some examples. Okay, so here they are. We're not gonna do them, we're just gonna read what they have to say. So the first series here is, it's an alternating series, right? -1 to the power of n plus 2 over n squared. So if you take the absolute value of this series, actually, let me just have something to write with. Right, let's use green. So if you take the absolute value of -1 to the power of n plus 2 over n squared, then you're going to get 1 over n squared, right? And that's a p series, and this p series is convergent. So therefore, we can say that this series is absolutely convergent, which means it's also convergent. Okay. All right. Let's take a look at this example here. So this one, let's see what happens if we take the absolute value. So absolute value of -1 to the n over n, that just gives you 1 over n. And 1 over n, that was one of the special series that we looked at in an earlier chapter. So this one is called the harmonic series. And then if you remember what we said about the harmonic series, we said that it was divergent. Okay, but the series itself is not a harmonic series. It was only a harmonic series because we took the absolute value. But the series itself is an alternating harmonic series, which according to the internet is actually convergent. We didn't go through that, but just accept the fact that it's convergent. So this is an example of a series where when you take the absolute value, it's divergent. But when you don't take the absolute value, it's convergent. So this is an example of what you would call conditionally convergent. Okay. There's not actually that many examples of conditionally convergent series. This is like the most famous one. So don't worry too much about that. And then the last one, we have sine of n over n to the third. So if you take the absolute value, then this gives you, well, sine just goes from -1 to 1. So if you take the absolute value of that, then it just, it sort of becomes less than 1 over n to the third. Less than or equal to, actually. And then 1 over n to the third, that's another p series, right? So that's convergent p series. So if you're less than a convergent p series, then you're also convergent. So this is absolutely convergent, which also means convergent. Okay, so those are just examples of those definitions. So these definitions will come in handy for the second test that we are about to learn in this section. Okay, so what is the next test called? So the next test is called the ratio test. Okay, why is it called the ratio test? That's a very good question. I'm glad you asked. So let's read it first. Suppose we have the series A of n. So define L as the limit of limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. So let's just take a look at the inside part. So a sub n plus 1 over a sub n. That's basically saying take the ratio of the next term over the current term, okay? So if you take the ratio of the next term to the current term, and you take the absolute value, and you take the limit you'll get will determine whether or not we have, convergent or divergent. So yeah, just take a moment to jot that down and we'll see how it works. All right, let's read how the test is concluded. So you have the limit, which we call L, and it says if the limit is less than 1, then the series is absolutely convergent and therefore convergent. If it's greater than 1, then it's divergent. And if it is equal to 1, then it's inconclusive, basically. Okay. So, you know what? Before we start on examples, let's try to intuitively convince ourselves why this test works the way it does. So we're not going to do a proof or anything, but let's think. So let's say the limit, or not the limit, let's say you get the ratio, right, of the next term to the previous term, and it was greater than 1. What does that say about your series? Well, I mean, according to the test, is divergent, but like that's not what I'm asking. So, like if you have, so the next term over the previous term is greater than 1. What does that tell you about like the numbers in your series? Like, are they getting bigger or are they getting smaller? Yeah, they're getting bigger, right? You can sort of think of it as like the common ratio. So the only way that the ratio can be greater than 1 is if you have a series such as like 1, 2, 4, 8, 16. Well, if it's a series, they're supposed to be added together. So this series here, if you take the next term over the current term, this would be 2, right? Because it would be like 16 over 8 or 8 over 4 or 4 over 2 and so on and so on. So if you have this situation, you can sort of see why it diverges because you're essentially just adding bigger and bigger numbers. And then if the ratio is less than 1, then it's convergent. So yeah, I mean, you can sort of think of it as like a geometric series. So if the ratio is less than 1, that means the terms get smaller. So therefore, you're adding smaller and smaller numbers, which gives it a chance to be convergent. And then if L equals 1, then it's inconclusive. So that's sort of like an intuition as to why this test works. It's not a proof or anything, but just to convince yourself. Okay, so Let's take a look at how we can use this for some examples. All right, so let's do these. Okay, so the first question is that thing. And then we just paste the limit we have to take for all these questions. So it's up there. All right, so we want to take the ratio of the next term to the current term. So we can write it like so. Let's go to the first one a little slowly. So a sub n is basically, oops, basically this thing right here, right? That's a sub n, is that. And then a sub n plus 1, that's basically the next term. So it's the same thing, it's just wherever you see an n, you're going to replace it with n plus 1. So I'm going to have to manually write this. So this is negative 10 to the n plus 1 over 4, 2 times n plus 1 plus 1 times n plus 1 plus 1. Okay, so that's a sub n plus 1. Okay, and now we have to take the ratio of these two things, which is probably going to get messy, but that's okay. So we're basically trying to divide two fractions, right? So this goes on top. So a sub n plus 1 divided by a sub n is basically this. And then we're going to divide it by a sub n. But if you guys remember, we can just write it as multiplied by the reciprocal. So I can write it like this. Divided by this goes here. And then this goes here. All right, is everyone still following? Yeah, okay. Yeah, I mean, we're just, it's kind of messy, but essentially we're just trying to, we're just trying to write this part out. So we're trying to write this. So a sub n is this, and then a sub n plus 1 is this, and then we just have to divide them, which gives us this. So now what we want to do is, well, since we're going to take the limit eventually, it's probably better to simplify this. So let's see how we can do that. Okay, so from what I see, I can rewrite the negative 10 as negative 10 to the n times negative 10 to the first power. And then in the denominator, this will be 4 to the power of, I'm going to simplify the exponent here. So that's 2n plus 2 plus 1. So it's 2n plus 3. And then here I have n plus 2. And then let me just keep this thing the same. Okay. So that looks fine so far, I guess. Let me rewrite the 4 to the 2n plus 3, because I think I can see something that cancels out. So let me write it like so. I'm going to get rid of this part. And then I'll write it as 4 to the 2n plus 1 times 4 squared. Is that okay? You guys are convinced that's the same as 4 to the 2n plus 3. So what I did was I rewrote this as this. There's no parentheses. I'm sorry. What are you referring to, Devin? Did I make a mistake somewhere? Two n plus. Are you talking about over here? Oh, so yeah. So a sub n plus 1. What that means is you go to where we see an n and you replace it with n plus 1. So yeah. Okay. But anyway, this is where we are now. So at this point, there should be a lot of things that cancel out. So what cancels out here? Let's simplify this. I see negative 10 to the n on the top and the bottom. And then this cancels out with this, right? Because I purposely wrote it like that. So let's see where we're at now. So we have a negative 10 on top, and then we have an n plus 1 there, and then we have a 4 squared, and then we have a n plus 2 there. Okay, so this is what we have now. Recall that the test wants us to take the absolute value, so let's do that. So if we take the absolute value, then it's like this. Okay. The test also wants to take the limit, right? So let's do that as well. So limit as n approaches infinity. Can you guys see what the limit is here? Yeah, it's 10 over 16, right? So the reason why that happens is the n plus 1 over the n plus 2, that goes to 1 as n goes to infinity. So you just have negative 10 over 16. But since we're taking absolute value, it's positive 10 over 16. Okay, so we have our limit. This is basically like your L for the test. So going back to the test, if our L is 10 over 16, what does that mean? I don't remember what it said. Let me just go back. Okay, so here was the conclusion. So based on our number, what can we say? Absolutely convergent, right? And therefore convergent. Yeah. So number one, this is convergent. Okay, great. So that's how you use the ratio test. This one is more the more messier ones. Not all of them are this messy, but hopefully you guys get the general idea. All right, let's try the second one. Okay, so again, we have to take the ratio. So this would be A of n is, so A of n is just what it is, right? It's what you're given. This is the current term. And then A sub n plus 1, that's n plus 1 squared over 2 times n plus 1 minus 1 factorial. You guys remember what factorial is, right? Yeah, so factorial basically means to multiply by the next integer down and the next integer down all the way until you get to 1. And that 1 factorial is also 1, and a 0 factorial is also 1. Okay, so that's factorial. Anyways, let's try to take the ratio now. So it's going to be A of n plus 1 divided by, or times the reciprocal. So times 2n plus 1, or 2n minus 1 factorial over n squared. Okay, so the goal is always the same. You want to simplify this as much as you can until you can take the limit. So let's see what simplifies. I'm going to rewrite this first denominator here. So n plus 1 is fine. If I do 2 and I distribute it, I get 2n plus 2, and I do minus 1. So that's 2n minus 1 factorial. Oh, interesting. Okay. Is that right? No, I don't think that's right. It's plus 1. Yeah, it's plus 1. Okay. Yeah. All right, so that's the denominator. Okay, so let's see if we can cancel out anything. So just by looking at it, do you guys see anything that cancels out? 2n minus, oh yeah, sorry, mixed it up. Yeah, they shouldn't be the same, so yeah. All right, so here is the trick. So the first denominator, we can actually rewrite it. If you write out the factorial, this is what it becomes. So it's 2n plus 1. Factorial means you multiply by the next integer down. So the next integer down would be actually 2n, just 2n. And then the next one is 2n minus 1, and then 2n minus 2, and then so on, right? Is that okay with you guys? Whoa. Yeah, so yeah, factorials. Factorial means like 4 times 3 times 2 times 1, which basically means 4 times 4 minus 1 times 4 minus 2 times 4 minus 3. So if I give you n factorial, this means n times n minus 1 times n minus 2. So if I give you 2n plus 1 factorial, it's this thing. But anyways, what's the whole point of all this? There's actually something that cancels out here. So do you guys see how, let me change the color. Do you guys see how 2n minus 1 factorial is actually over here? Alice, why can't we write it as negative 2n minus 1 factorial? I don't think you can. Is that a property of some sort? Yeah, I don't think you can do that. Okay, but yeah, so these two cancel out, which gives us a simpler expression. So let's see what's remaining. So we have a sub n plus 1 over a sub n. What's left is the n plus 1 squared over 2n plus 1 times 2n, and then there's the n squared at the end. Okay, all right, so this is what we're left with. Let's go ahead and take the absolute value, and then let's go ahead and take the limit. So when you take the limit, what do we get here? Yeah, you get 0, right? Because the degree in the denominator is 4 and the degree in the numerator is 2. So this goes to 0. Okay, what does this tell us about the series? Yeah, so absolutely convergent. So remember, when the limit is less than 1, we get absolutely convergent. So this right here is convergent. Okay. So yeah, do make sure you know how to work with factorials. Okay, let's do the last one. Let me just crop this. All right, so here's the last one. So the previous two examples was where the ratio test led us to convergence. Let's look at an example where that doesn't happen. So let's look at this one right here. So let's take the ratio test, which means we have n plus 1 plus 2 over 2 n plus 1 plus 7. I'm going to go a little bit faster because you guys have seen this process 2 times. So it's times the reciprocal, right? So it's 2n plus 7 over n plus 2. And then we have n plus 3 over 2n plus 9 times 2n plus 7 over n plus 2. Yeah, I don't think anything cancels out here. So we just have limit as n approaches infinity of the absolute value of n plus 3 to n plus 7 to n plus 9 n plus 2. Okay, what's the limit here? Can you guys see it? Yeah, so because the degrees are the same, you just take the leading coefficients. In this case, it would be 2 over 2, so that would be 1. So the limit is 1, and then according to the ratio test, when the limit is 1, it's inconclusive. Okay, so that means we need to do another test here. So for this example, what's the test? The ratio test failed, which means we need to do another test. So any suggestions? What test? Divergence test. Okay, that was you seem confident in the speed you used to suggest that. Okay, so if we were to do the divergence test, we've had limits as n goes to infinity of n plus 2 over 2n plus 7. This gives you 1/2, which is not equal to 0, right? So this diverges. Very good. So yeah, we probably should have just done the divergence test in the beginning, but it's all right. Okay, so that's the ratio test. The next step will be to give you guys some examples to work on yourself, but we're actually going to stop here today, and we'll do the rest of this section on Thursday. Okay, so this is done for now. Everyone have a good night, and I will see you on Thursday. Class dismissed. Yeah, there is a homework for this, but you don't need to do it yet because we're not done with this section.